Welcome to our training session about electrochemistry, electrochemical sensors and electrochemical interfaces. I'm Lutz Stratmann. I'm with PalmSense, a partner of ADI. And yes, I think we're all missing real-life conferences, so we should do something here that we really like doing at real-life conferences, and that is drinking some nice wine. But actually, I wouldn't drink that wine, because I've prepared this already with some vinegar for a stable pH and some salt for conductivity, because I would like to show you an electrochemical experiment. So what we're going to do today is I'm going to use a tablet and our small potentiostat, the Sensit Smart, to make something like an electrochemical fingerprint of this wine. Why would you want to do that? Well, as you know, there have been cases of adulteration of wine, for example, or maybe that somebody wants to say that a wine is a certain wine because it has a high price, but in fact it actually isn't. What we're going to show today is a rather simple measurement where I want to show you the difference between red and white wine. So first, about the measurement. I'm doing a cyclic voltammogram, so I'm going to increase the potential from a reducing potential to an oxidizing potential, and we're going to see what can be reduced or oxidized in this wine. White wine is, well, white because it's missing some components from the shell of the grape. From the peel of the grape. While red wine does have these components, and many of the components in red wine are complex aromatic molecules, which can be, oh, now I'm switching the wine, we're already done with one measurement. You can follow that, by the way, with the red light that you see in the front of the instrument. So red wine actually has more of these complex organic molecules that can be easily electrochemically oxidized. So we will see in the higher potential ranges for the red wine a higher current that is then showing clearly the difference between red and white wine. This is now a very simple approach for this measurement because the electrodes have not been designed in a way that they are selective for certain molecules, etc. You could also do that, use multiple different electrodes that are selective for certain types of molecules or species, and this way creating an electrochemical fingerprint of the wine. So you could store, for example, in a database, the different fingerprints of the wine to make sure nobody can sell you a certain wine for a different one. Or maybe you're just looking for pesticides or other things that just don't belong into wine. And we're already done with our measurement. I just make sure you can nicely see the measurement. And yes, we will put the screen capture in the video, so we will always have been able to follow this. Okay, so this was the experimental part to show you how exciting electrochemistry can be, and now I'm going to tell you a bit more about the theory behind what was just happening. So maybe, because I said I'm not with ADI, I'm with PalmSense, so maybe you want to first know, okay, what is that company PalmSense? Well, PalmSense is a company from the Netherlands. We're in the Netherlands. We have been founded in 2012 under the name PalmSense. However, PalmSense is a successor company of the company Palm Instruments, which have been founded in 2001. There was a management change, and so we have decided to start fresh with a new name. We're shipping to over 100 countries worldwide. Some of them have distributors, but to many countries we're shipping directly. Our main products are electrochemical measurement devices like potentiostats, galvanostats and impedance analyzers. So devices that apply potential, measure current, apply current, measure the potential, or measure the impedance and phase shift of an electrochemical system. Our customers are from academia or industry, so we have researchers and developers who buy our products, so people who really do research. They are using our instruments, to do fundamental research, and we have people who, develop instruments around it to make commercial products. Yes, our advantages our relationship with ADI is that we are a partner, so we're part of the ADI Alliance, and we're a pioneer in the Build with PalmSense project. You will see that because I think actually the Emsted Pico that we have created together with the ADI is one of the first products that was released in the Build with ADI. Okay, so let's go back to the basics of electrochemistry. And I think many of you won't be chemists or maybe even didn't like chemistry in school. So here's a rough introduction. I think most of you are aware that chemistry is all around us. There are reactions happening everywhere. And I have a few examples here. And the examples that I have here are oxidations and reductions. And a chemist says reduction is taking up electrons, while oxidation is the donating or losing of electrons. That's kind of a point of view question. Most of the times you have reduction, oxidation happening at the same time. So just in the nature around you, what kind of reactions can you see? Well, the oxidation of steel, where you form rust, is a classic oxidation. Then the turning green of copper is an oxidation. Fire is basically an oxidation of random organic molecules. The turning brown of an apple is an oxidation with the help of an enzyme in the apple, right? Even inside you have an oxidation. You have the digestion of sugar. And if you think about it, you're basically burning sugar. You're taking in sugar and some oxygen, and you're breathing out CO2. So you basically burned inside your body the sugar. Bleaching your hair is also an oxidation, just a bit unspecific, but it's mainly affecting your pigments. Reductions are a bit more difficult to find in an isolated way, but prominent examples are photosynthesis, where you use sunlight to create out of CO2 sugar. You create sugar, and then the plant uses that. And another example that maybe you know from your household is cleaning of silverware. I mean, most of us don't have silverware out of actual silver anymore, but some people might have, and they know it's a tedious task to clean the silver because every now and then it gets this layer of oxidation products, right? And a trick to clean it is cooking silverware together with aluminium and salt in water, and you get clean silver. And that is a redox reaction because the aluminium gets oxidized and the silver reduced. And in nature, all electrons donated must be accepted. So actually, all these reactions always appear in couples. So you need always an oxidation agent and a reduction agent. However, I mean, we have developed more technology, and we got to the idea, why not replace one of the oxidation or the reduction agents with electronics? So the idea is that electrons or currents now become our reaction agent, and this way we can control the reactions. Or we can just observe, we provide a certain potential and observe the current, and this way study and understand the chemistry with the help of electronics. So in the bottom of this slide, you see very nicely on the left a cyclic voltammogram in a very classic way for, like, I'd say the ideal substance. So this is how they look real nice. And on the right side, you see this cartoon that shows you how a substance would be oxidized, for example, at an electrode on the interface. Right. And I've just shown you one application, but there are many applications out there for electrochemistry. How I divided it here is can be disputed. There's no like general agreement what fields of electrochemistry are there, because they're obviously all interlapping and they're like very interdisciplinary. So, but here are three that I think most people agree on that are there. One is electroanalysis. That is how much of species X is in solution Y. That's the question you ask, and electroanalysis will give you the answer. Classic examples of that are, for example, well, water quality analysis. You can look for heavy metal, pesticides, or fertilizers in your drinking water that you don't want to have there. We can also look at food quality, again, looking for pesticides, for example, or how much a certain sugar is in that food. So how do you process it further? In vitro diagnostics is very important, as we all know. In the last year that has become very prominent, because we want to know how much of is a certain virus or bacteria present in a sample. Do I have a certain sickness? Also, therefore, there are electrochemistry measurements. Corrosion is an important field of electrochemistry. Because there's a lot of costs involved. If things corrode, they need to be replaced, they need to be painted new, etc. And electrochemistry can help there. Classic corrosion tests are still spray salt tests. So they put them in a room and it can rust for a long time, and then people look at it and say, oh, it's rusty. And that's not super efficient, because electrochemistry can help you picking these materials further, evaluating new materials, new coatings, or help you develop new techniques for corrosion protection. The last field that I want to mention here is energy conversion, because it has been very big in the media. It's very important because it includes things like batteries, fuel cells, or solar cells. I've put on the bottom a little indication of what the solution that I present to you today will be capable of doing. So in the field of electroanalysis, such a small potentiostat is more suitable. One thing is because usually currents and potentials are on the lower end in these type of applications, and such a small potentiostat is also usually on the lower end of potentials and currents. In corrosion, it can be very mixed. Sometimes they need lower potentials and currents, sometimes higher. And in energy conversion, well, you can't drive a car with 3 milliamp, can you? So, this is what we will show you today. And since I said electroanalysis is the most interesting one for the solution that we show you, I would give you like some more examples of applications. The best known example out there is the glucose in blood measurement. Like everybody knows this. Everybody knows a diabetes patient who does it regularly. That's an electrochemical test. You can also, of course, measure glucose and sucrose in potatoes. That's what one of our customers is doing. You can measure lactose in milk, or nitrate, heavy metals, or pesticides in drinking water. These are all projects that our customers are working on or actually having already gone to market with. You can also compare corrosion rates. This is another common thing to select materials, or do COVID-19 detection. You can imagine that in the last 2 years we got a lot of customers who do want to do this, who want to detect COVID-19, and they're very close going to market. Alright, now that we know all the applications, let's talk about potentiostats, because in the end that is the solution that we offer here. A potentiostat is in principle a very precise power source, and it allows you to apply a potential at your working electrode, that is the electrode you will be interested in, versus a fixed point, which is the reference electrode. And then if you would have, well, again, chemistry is playing here, if you would have a current flowing between the working and the reference electrode, the potential of the reference electrode would change, and you don't want that. You want a known fixed point. So we introduced a third electrode, the counter electrode. So the current flows between the working and the counter electrode, while the potential is applied between the working and the reference electrode to keep the reference electrode current free. This is a potentiostat in a nutshell, and I want to give you just 3 examples of popular electrochemical techniques to show you the variety that is there in electrochemistry. Cyclic voltammetry is what we've done just now. We made a linear potential sweep in a certain direction, and then we have, with the same slope, we just made the slope negative, so in the other direction, we swept again our potential. What you get is, over time, you see that on the left, the potential versus time, and then the current over time. When you get close to the potentials where reactions are triggered, you suddenly get an increase in current. What you then plot is you plot the current versus the potential, which you see on the top right side, and that is very nice, because this is a very versatile technique to characterize species. The peak position, the potentials, so the shape of the whole CV is usually very characteristic for certain species, right? Sometimes it was called, or in the past it was called, the electrochemist spectroscopy before impedance spectroscopy became very popular. You can get kinetic information, it's very fast, you can get a quantitative signal, so you can use it also for electroanalysis, and you can, for example, identify catalysts or redox mediators, or can make surface modification at the same time while you're monitoring it. It's a great technique. But sometimes you need more sensitivity, and then you look at techniques like differential pulse voltammetry, where you combine a potential sweep, a linear one like you've seen it just now, together with pulses. And there the idea is that you jump backwards and forwards to reduce the depletion in front of the electrode. You can imagine when I start continuously to react something at the electrode, it will be depleted. But when we then make a small jump backwards, we produce again what we've depleted a bit, and we give the other solution a bit time with diffusion to bring new species to the electrode. And what we do here at differential pulse voltammetries, we don't plot the current, but we plot the current differences right before and after the pulse. This is the nice effect that we get rid of some physics effect and only look at the chemistry. And what we get this way is, well, we also get like a differential plot of what usually would like a linear sweep will be, which has the advantage that we get a symmetric peak, we get a peak that is proportional to the concentration in our solution, and as I mentioned, it's very sensitive. The last technique I want to have a look at is electrochemical impedance spectroscopy. I think many electronics engineers are already familiar with impedance spectroscopy, so I can keep this brief. You apply a potential sine wave and then you look at the current response, which is usually a current sine wave, and you use the two sine waves to calculate the impedance the impedance and the phase shift. It's a very interface sensitive technique because the impedance reacts to the changes that are at the interface, and the reactions are going across the interface. Usually what you do is you scan the frequency of the AC potential that you apply, and then you plot for each frequency the impedance. And then you have to, find a way to plot this huge amount of data. A very popular way is the Nyquist plot that you see on the bottom left, where you have the negative imaginary impedance plotted versus the real impedance. And the shape of this Nyquist plot is often very characteristic for certain effects that are happening, and you have a good idea of what your system is doing. With equivalent circuit fitting, that means you take your real chemistry system and think for each of the components of it that give a contribution to the impedance, you think for each of them of an electronic component replacement. So that is what you want to do. You want to replace each of them with an electronic component that you understand. Then you simulate the impedance spectrum of that circuit and try to adjust the parameter that fits. And this way you can extract the contribution of single elements. This way you can, for example, detect corrosion before it's even visible, check if your coating is working, for example, is it taking up water? Or you can make label-free immunosensors. Label-free means often, for example, if you look for a certain DNA, you have to attach like another molecule that will give a nice electrochemical signal. With impedance spectroscopy, the change of the interface due to interaction of certain molecules can be large enough to have a good signal without introducing any labels. All right, there is a bit of a disadvantage. It's a rather complex technique, and you have to invest quite some knowledge to analyze it properly. Okay, these were just some techniques for electrochemistry, and you see already like how many applications there can be for these. So now I want to talk about the solution that we want to offer you, which is the EMSTED Pico. Okay, let's have a look at that. So, in the past, potentiostats were of course very large. That was the analog age. Potentiostats were large. Even the first digital potentiostats were large, and actually they still are, because they have many companies work on the performance and power of the potentiostats, while the company PalmSense has always worked on making potentiostats portable and smaller. And so, together with ADI as a partner, we could create a very small potentiostat with 18 millimeters by 30 millimeters that can be used as OEM potentiostat, meaning you would somebody give this module and they can build it into their device as the electrochemical core, you can say. Right. The EMSTED Pico has two sensor channels where you can connect your working reference and counter electrode, so 2 times. It has up to 8 GPIOs, it has 3 analog inputs, you can have a digital data output, UART connection, you have SPI connection and an I2C connection. The parameters of the EMSTED Picos are very good for its size, but of course if you compare it to the very large potentiostats, it has a smaller potential range. but and what is very impressive for electrochemical devices with this size, it can go to up to 200 kilohertz while doing impedance spectroscopy. It can record up to 1,000 data points per second. Right, and also what is very good for these portable or on-site and point-of-care applications is you can put the MSTED Pico to sleep, so it's hibernating and it's using just a very low amount. It's just using 35 microwatts of performance until you wake it up to perform your measurement. Right. For those people who are more into block diagrams, I have your block diagram where we also indicated some parts of ADI that we used. And yeah, I think for those who are interested in that, just pause the video, take your time looking at it. We're just moving on here because I want to show you the MSTED Pico development kit. Together with this module, we have developed a development board that gives you some advantages while developing. There's already an MSTED Pico for you soldered onto the board, so we reduced already the risk of damaging it. There's a USB connection for power and communication, so you can start immediately just by connecting it. There's also a Bluetooth connection and actually a battery holder underneath, so you can also start working wireless immediately. You can get the MSTED Pico development kit at Arrow, DigiKey or Magnica, so you can actually order it now, start now and work on electrochemistry. Well, maybe you want to know a few more things about it, because we talked up to now about hardware, but you might ask like, well, software is complicated as well. Well, not with the MSTED Pico. The MSTED Pico comes with a firmware that already supports 10 different measurement techniques. When you record data, you can store it on an external SD card, on the internal flash, or just use data streaming to save it like to anything. We offer you software development kits for many platforms, so you can easily write your own software with the help of our code examples. You can easily actually translate also your code to new platforms if that's what you want to do. And in our end user software, you can generate the code piece that you need to perform your technique. Talking about end user software, that is actually also compatible with the MSTED Pico. So you can immediately just install our end user software and start measuring. Your hardware developer, your researchers, they don't need to wait for your software developers to make the first interface. They can just use our end user software and then use that, well, for everything, for setting up the parameters and script, performing the measurement, and save and export the data. You can see on YouTube some videos where we show the software as well. Our channel is just PalmSense, so maybe leave a like and a subscription there. Okay, as I said, you can use that to export a script. That script will be in the language MethodScript. And MethodScript is very easy to use because the MSTED Pico has an onboard parser. It's human readable and it allows you to combine easily electrochemical tasks. And you see in that little gift running here how the communication basically works. It's just a short checking in by the host. Hey, are you an MSTED Pico? It says yes, and then I have a script for you. Here is the script. And then once the script is okay, it will start to send you the measured data. So very easy to use. If you think the MSTED Pico might not be suitable for very high volume customers because they think it might be in the price too high, they want to reduce it, well, you could also buy the MSTED Pico Core. What is the MSTED Pico Core? Well, actually, it's just the ADU CM355 with our MSTED Pico firmware, which will make sure that the customer can immediately do 10 electrochemical techniques. And remember, it includes electrochemical impedance spectroscopy. While the chip is just 5 by 6 millimeters in footprint, it supports MethodScript this way and works with our SDKs. So it's ideal for high volume applications. People can start with the MSTED Pico, and then when they realize they need high volumes, they can start to work with the MSTED Pico Core. And that is already, well, everything I wanted to tell you today. I would just want to give you some closing remarks with a bit of a take home, because maybe you want to try this at home. The company Zimmer & Peacock, or short Z&P, offers carbon electrodes together with a series of kitchen chemistry experiments like the wine thing that I did today, or maybe you want to detect caffeine or vitamin C. And the nice thing about these experiments is that you can do them at home because it uses non-toxic solutions that you can put down the drain and you don't have to worry. You don't have to get rid of heavy metals or acids or these kind of things. Yes, it can be performed with the Sensit Smart, as you saw today, so there should be nothing holding you back. And just a small summary, because it is a long presentation, I understand. The topics that we addressed today are electrochemistry and how you can use it to control and observe chemistry via electric current. You can use the EMSTED Pico especially for electroanalysis, but also, well, for the broad selection that there is of electrochemistry. Just to again remind you of some cool applications. You can detect like COVID-19 or other diseases at point of care measurements. You can measure, for example, corrosion or look at food quality. All right, then, yeah, just again as a reminder, the EMSTED Pico Development Board is a great way to kickstart your development. It's available on Aero, DigiKey or Magnica, so the usual ADI distribution. Okay, thank you for watching. I hope you enjoyed the video and have a great conference.